Greetings, welcome to another video. So if you followed along with a previous video, I was trying to repeat the voltaic pile of volta, which is alternating layers of copper and zinc with a dielectric in between. And sometimes people use paper or tissue, or the dielectric can be whatever insulator you have, and I happen to choose wood as the dielectric because I had balsa wood lying around. And as I got busy with it, I started finding, I can't get a consistent value. And what I finally realized is that when I was pressing on the thing, the voltage was changing. And so I realized, and I hadn't known this when I started, my gosh, wood is actually a piezo or piezoelectric material. And so this is something that's really grabbed my attention. And I've been looking at, what are other piezoelectric materials? And quartz, which is primarily what sand is made of. It's either very pure quartz, I think that would be more like the white sand kind of beaches, or it's 70% of the sand is quartz. So that's another piezoelectric material. But as I thought about it some more, I was thinking, I'm like doing this on a little table here, and with a meter. Did I really see piezoelectricity with wood? And so for the first time, just earlier today, I just put in piezoelectric wood in Google. I did know, like bone is piezoelectric. I knew that from medical school. And so I figured, yeah, wood must be piezoelectric, but I never searched on it, and I'm glad I did. And so why don't we just go through a couple of these articles, and then I'll show some more of the piezoelectricity experimentally. There's really just going to be a lot to do with that, and I'll kind of talk through that as well. But let's spend a minute just looking at these. And I've only glanced at like 2 or 3 of them, and I should probably read a bit more on this. So let's just start with the first result that shows up with piezoelectric wood. Piezoelectricity as a fundamental property of wood from 1968. So if we go there, Wood Science and Technology. What a great journal. So the piezoelectric effect in wood, i.e. the currents of electric polarization, i.e. a voltage, under mechanical stress, and also mechanical strain and electric field. And then they just go into the theorizing. Consider it was accounted for by the uniaxial orientation. Unfortunately, all we have is the abstract or summary. But what we get from this, because it just immediately goes into theory. What we get from this is that, piezoelectricity is documented in wood. We get one good data point. The value of the piezoelectric modulus for wood was approximately 1/20th that of a quartz crystal. Now, again, I'm not a wood science and technology guy, but I would say piezoelectric modulus means how good it is. So I think that they're saying wood is 1/20th as piezoelectric as quartz. And I should read up on piezoelectric modulus. But that, I think, is what they're getting at there. Let's go now to the third result, wood that generates electric voltage. This one was really interesting. And the Innovation Society. But they're researchers out of Zurich and EMPA, I don't know where that is, have chemically modified wood and made it more compressible, turning it into a mini generator. When a load is applied to it, an electric voltage is generated. So I sometimes find some of the language a little bit vague. They're saying it turns it into a mini generator. When a load is applied to it, an electric voltage is generated. Now, conventionally, when you're thinking of a generator and a load, you're thinking of an electric load upon a generator. That's not what's being said here. It means that if you take this material and put it under a cinder block, it just sits there with an electric voltage that puts out, amperage. And it could serve as a biosensor. So it couldn't serve as a biosensor unless it was also putting out some amperage. And they always then, immediately go into it as, oh, this could be useful as a sensor, ignoring the, huge pink elephant in a top hat riding the unicycle, that you have something where it's stressed, say under a cinder block, and it just sits there perpetually churning out amperage across a voltage difference. Sure, it's small, but it's sort of, well, that kind of presents some issues. So again, it's a small effect, such as you would use with a biosensor or something. But something like the Casimir effect is a very small effect, and that gets a lot of so shall we say, publicity is like, oh, this doesn't follow conventional physics. Well, this is problematic too. If you just have something where you put it under a cinder block, and as long as that stress is there, it's going to put out a voltage, then that's kind of a problem. But I'm starting to ramble, so let's go further into this, and this is why I really got kind of excited about this. Ingo Berghart's team at sort of immediately thought of Ingrid Bergman. Ingrid. At ETH Zurich have shown that wood is a surprisingly versatile material, so on and so forth. Now, Berghart, not Bergrid's. Where do we get to it? To convert wood into an easily formable material, you can remove the lignin. And so I thought, there's going to be all involved and whatnot. The members achieved the delignification by placing the wood in a mixture of hydrogen peroxide and acetic acid. And that's what really got my attention. I have hydrogen peroxide. I brush my teeth with it at night. I don't have pure acetic acid, but I have apple cider vinegar, which I think is going to be primarily acetic acid. And I imagine I could pick up some pure acetic acid, but I'm pretty sure apple cider vinegar, I'll have to look it up, but that's mainly acetic acid. So, you're telling me I just got to put the wood in hydrogen peroxide and apple cider vinegar and let it sit there for a while, and then we get down to it here. It becomes sponge-like. The wood sponge generates an 85-fold increase in the piezoelectric voltage compared to native wood. So this was really the main article I wanted to talk about. And they're saying they're getting 0.63 volts out of it, and they compressed it 600 times. And then they're talking about 30 wooden blocks connected to each other. And that's been in the back of my mind the whole time, is how do these piezoelectric materials behave in series and parallel? What are they gonna do? But it sounds like you can put them in series. So they're saying that then you can operate like a computer monitor from the person's butt sitting in the chair, I guess. Which is really kind of a cool idea, because you have sort of this cushion on the seat, and sitting on it, then you generate the electricity to operate the display for the computer. And then they did some more with the fungus. I don't think I want to play around with the fungus. So that's the exciting one. And then there was another one. This is about as far as I got. Wood and zinc oxide. This caught my attention because, again, I started this trying to reproduce the copper zinc battery, and I was also thinking like silver zinc, and I can't remember, it's either you're going to end up with silver oxide or I think it's zinc oxide. So this one's interesting too, although that's about all there is to it. is they were getting 1.3 to 1.4 volts with zinc oxide treated wood. So that's interesting if you have zinc oxide forming as a half reaction in a battery. And really, not to ramble too much here, but I'm going to go back to the voltaic pile, but I want to explore this for a while. But one of the things that I'm seeing is that the piezoelectric effect, when you're using dissimilar metals instead of just two identical metals, doesn't seem to be simply additive. It seems to be synergistic with the battery. So in other words, you have say a zinc copper battery that's putting out, I don't know, let's say a milliamp, and you press on it and now it's putting out 3 milliamps or something like that, which is a much bigger effect than you'd be seeing just from, if you just had the two copper strips alone. So it seems to play nice with batteries, and that's something that I want to follow up on. But there's just a lot to do, and got to do it hopefully fairly methodically. So I'll go back now and I can show you some of the things I've seen, again, just with two copper plates and a piece of balsa wood and some water. And then what I did this time is I looked at the same thing, but I changed from water to distilled water to an acidic solution to a basic solution, and it changed the behavior a lot. But the whole time I'm only using two plates. So again, a battery is visualized as electrochemical with two half reactions happening because of the difference in electronegativity, or how much each plate likes to obtain or release electrons. So when you have two copper plates, there shouldn't be anything unless you're getting this sort of piezoelectricity. But what I found fascinating and what I looked at this time is that the behavior changes depending on whether you're using tap water, acid base, or distilled water. And I don't really have a good explanation, but I would say that I don't think with any of them you would ever see the copper plates dissolving, because there shouldn't be any electrochemical activity going on at all. Now, someone who is much more versed in chemistry might say why that is not the case, but even if it is the case, I would suspect it would be trivial. But again, you got to just have fun and look at these things. So I'll show you what I was looking at now with this stuff, and then as I said, I'm going to go on and do more with this. And ideally, what I think would be really cool is to end up with a rechargeable battery where you're sort of enhancing the output, and there's also sort of a baseline output due to piezoelectricity. Okay, so on to the experiments this episode.
Okay, why don't we start with this then? And this is actually really good. I apologize about the noise in the background. I'm distilling some water, and so that's going to be part of this as well. What do we have here? We've got a piece of balsa wood, and we've got two plates of copper, both the same material, 2 plates of copper. I just wrapped a copper wire around this one because it was a little awkward. And so that's going to a volt probe, and this is going to a volt probe. And then this was actually an idea from someone on the YouTube channel, and so thank you. Was instead of pressing on it, just let magnets do the pressure to stress the thing. So let me back up a little bit and say I was doing a little bit with sand, but it was only very, very small piezoelectric effect that I could see, and it's sand, so it's like, how do you keep it in place? And I've got to think about that. I mean, you could like run tape or something, but it also needs to be able to compress, so you can't just have like a box. And then I went to this is a Rochelle salt crystal. It's kind of broken now because I've been pressing on it. And Rochelle salt crystals are piezoelectric. But it wasn't, tremendously piezoelectric. So then I was like, well, what was I seeing before? And so I went back to just using a piece of wood, and I squeezed it down with these, and I hardly saw anything. It was like maybe a millivolt or two. There's actually some interesting behavior depending on where you're touching things. And this is nice because you're not touching anything. So then what I did is I just dipped the balsa wood in a glass of water. And so when you do that and you stress the balsa wood, you have 2 plates of copper, right? So this can't be a galvanic battery. All you have is water-soaked copper, 2 plates of water-soaked wood, 2 plates of copper, and you're stressing the wood with pressure on it. So this goes to one end of the voltmeter, this goes to the other. Then you have this cap, which is shorted now by the white line. The yellow line is going to one plate, and the green line, if I connect it to the negative of the probe, would go to the other plate. So let's leave it unconnected now. We just turn on the voltmeter, and we're sitting at a cool 27 millivolts. Sitting there. Water, wood, copper, and again, that idea with the neodymium magnets, that's kind of cool. So it's really hard to say that anything that's going on is galvanic because it's 2 plates of copper. They're not dissimilar metals. The only other possible thought that I'm having is this was just tap water that I dipped it in. So maybe somehow the ions migrate such that you're going to get galvanic corrosion. And so that's why I'm doing the distilled water to see, does this go away with distilled water? But it's starting to look, I don't know what it is yet. It's starting to look like it's not a galvanic battery, it's a piezoelectric battery. But if it works with distilled water, absolutely. But even if not, I mean, I can't imagine a little bit of tap water is going to break down copper plates. But then again, you're only getting 27 millivolts and not, 800 millivolts or 900 millivolts like you would with dissimilar metals. But all that said, let's now connect. I'm going to disconnect the short. Let's connect the capacitor now across these plates. And so maybe I can even show them both at the same time. I'm going to do that right now. And it's back. And now I'll just like short it and see how quickly it bounces. Bounces pretty darn quick, doesn't it? Boom. 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 Now I'll just leave it shorted. Come on. Leave it shorted, leave it shorted, leave it shorted. It's shorted. Release. Boom. Shorted again for a long time. Release. Boom. So that's kind of neat. That's just copper, wood, water, and magnets. Now let's go ahead and just dunk the thing in some water. So now I've dunked it in water, and we're sitting at 52 millivolts, sitting there. And so now let's do the same thing. We're gonna I've shorted it, and now we're gonna connect it across there. I didn't even see it move. Okay, boom. Boom. And we're back to 51 millivolts. All with wood, copper, water, and batteries. So, I mean, the more I think about it, now it might go away with distilled water. I'm going to have to wait a little while and find out. But the more I think about it, I mean, the reason the plates dissolve are the two half reactions between the dissimilar metals. It doesn't matter the electrolyte. Like lead acid batteries, the acid or strong base. And so that's another thing I'm going to do is even with just keeping the plates identical is put it in a strong acid, put it in a strong base, and see what you get then. Because I can't see how the plates could corrode at all if there are no half redox reactions going on. How could they be going on? They're both copper plates. So that's what this is doing. Let's put in a big cap. So here's a 1000 UF cap as opposed to a 10 UF cap. It's shorted right now, but it's everything's connected, so I would like to charge. It's just charging across the short. So I'm going to remove the short right now. You look at that. I mean, that's a 1000 UF cap. It's just charging right up. And all you have is copper and wood and magnets. Do one last thing that's kind of neat with the magnet thing, because now you can kind of do a control group. I'll remove the magnets and just put it back in there, and we'll see the effect that the stress on the wood had. Okay, so now it's just got the pressure of the rubber bands, and instead of 50 I'm seeing 20, which that surprised me that even that's there. What I'm going to do now, because I was thinking, well, previously I was zapping things with 5,000 volts and whatnot, so I'm just going to start from the beginning again. I got two fresh strips, just cut them off copper, and a new piece of balsa wood. I'm just going to repeat everything from the start. See, this is just 2 plates of balsa wood. The wood's dry, and it's kind of just all over the place. I'm going to press on it. And it does change. It's going down. So there is even a little something when it's dry. Now I'm going to wet it with tap water again. Oh no, first I'm going to put the magnets on. No, first I'm going to wet it with tap water. Sound like the Rain Man. Okay, so I've wet it with tap water. Now, there's no cap or anything hooked up. And it's just the rubber bands there. And we see that. Pull it out. Back to there, which is just about nothing. I'm going to press on it by this here. Yeah, we see that. Now I'm going to put the magnets on. Pretty much the exact same as before. So it wasn't that I had like conditioned the copper or the wood or anything like that. This is fresh wood, fresh copper. It's got the magnets on now. We're sitting at 27 millivolts. Now I'm going to dip it in the tap water. And it's even a little higher. 67 millivolts, 68 and climbing. So now, oh, that's cool. I'm gonna put it on a cap real quick. So just to be sure, I hooked it up to a cap. I've got the cap shorted. I'm gonna remove the short right now. And the exact same behavior. I just find this really cool that you can get a battery just from the pressure from the magnets, 2 strips of copper, some wood, and some water. So, I mean, the thing going forward is going to be to actually have another, something more like a traditional battery with copper and then zinc, and then see if the same sort of stress thing does an improvement. But before even getting to that, the things to do are to run this in distilled water, and this may all go away in distilled water. Who knows? And then run it in, like apple cider vinegar or acetic acid, and run it in KOH. And maybe it does better. I don't know where it comes from. It's just coming from the stress on the wood. Okay, so new piece of balsa wood. I dried the copper. I even used a dry rubber band. Put this together. This is distilled water. So from the pressure of the rubber band, we're just sitting there at that voltage. Oh, shoot. Hold together. So now I'm going to dip it in distilled water, and I have zero idea what it's going to do. Hold together. Son of a gun. Now, get in there, stay in there. Doesn't look like it does that. Wait a minute. This is good. So we're sitting at 16.5 millivolts in distilled water, and I haven't even pressed it more than the rubber band. So now I'm going to put the batteries on. I'm going to put the magnets on. Well, it does seem like most of it's gone, sitting there. I'm going to dunk it back in the water. Okay, it's kind of as I expected, that most of it's gone. We're sitting there. It has some strange behavior. If I can show it, I'm going to like pull it out, and the voltage goes all over the place as it crosses into the water. It might have something to do with the surface tension on the water there. But it settles down to next to nothing. Well, not settling to about 12 or something like that. And when you put it, here I'll put it into a big 1000 UF cap, and it's slow. It does come back, so I mean there is current flowing, but it's slow. So I mean, what do you want to say? 80-90% of that effect is gone, and it was from the impurities in the water. This part, I would say, I can't think of any way that voltage can be electrochemical. That has to be from the stress of the magnets. Now, yeah, charge the cap up to there. But if it is augmented when there's ions in the water, does that mean then that that's electrochemical? In other words, plates are dissolving through galvanic corrosion. Maybe so, or maybe whatever's going on from the piezoelectricity is amplified. I don't know. And even if the plates were dissolving, if the pressure on the dielectric improves what you're getting out from your battery, then it's sort of like, well, who, pardon my French, who gives a fuck? If you have a zinc silver oxide battery, that's rechargeable. So just like with lead acid batteries, the plates, some stuff comes off the plates and then you charge it, they're back on, off. And same thing with any rechargeable battery, you just recharge it. But if you stress this dielectric and you get more amps out, then, that's more better. If it liked the ions in the tap water, got to do it. Let's put some sodium hydroxide in here. All right. Okay, so I'll even put a second capful in. Actually, eyeballing it, I think the one capful there is enough. So now granted, no dissimilar metals, just copper. What's it gonna do? I got no idea. Oh shit. Okay, so the polarity reversed, and we're sitting at -70. I'm gonna let that settle down. Oddly, it doesn't look any better than the distilled water. It looks worse. And as I did put in a little more of the sodium hydroxide, and the voltage went down. So I got to do one more thing. I got to put it in acid. Okay, so fresh batch of wood, and I cleaned off the plates. I have this ancient champagne vinegar. I don't know, can vinegar go bad and not be acidic? And then this is distilled water. So I'm going to pour this in here, and we'll have a weak acidic solution. And then I'm just going to cut to putting the magnets on and throwing it in there and seeing what comes out. All right. Okay, so before I dropped it in the acidic solution, it was sitting at about negative 30 millivolts. And then I dropped it in there. It reversed polarity, and it's climbing. Let's see if this is the best one of all. It's starting to look like it. Yes, indeed it is. This is really cool. That's coming up on 0.2 volts. And the acetic acid is weaker than sodium hydroxide. And you saw I only put like half of it. I mean, most of this was distilled water to start with. And again, no dissimilar metals. So it seems like it's not going to quite make a 1/4 volt. But, and I don't mean to sound like a broken record, but it's 2 plates of copper. They're just 2 plates of copper on a piece of wood. All right, kids, that's all for this episode. And pretty clear now, I don't have any clue about what I'm doing. But what you can see is that you can get voltage out of 2 identical metals. They don't have to be dissimilar metals, and that's the whole principle of how a battery works. So I'm saying it's piezoelectricity. I don't know what else to call it. I think that's what it is, and that would be piezoelectric wood, which is kind of odd in and of itself. But one thing that you can see, and you can repeat easily for yourself, I mean, it's not like I'm building a cyclotron here, is you can get voltage out of 2 identical pieces of copper. And at that, 0.2 volts, I mean, it's not like you're charging a cell phone, but it's not like, oh, that's just the, the multimeter being imprecise or something like that. So in any event, I mean, I think the next thing I'm going to do with this is I'm going to put in, copper and zinc, which gets back to the classic voltaic pile, and look at that with it stressed, with it unstressed, with different acidic or basic solutions, and go from there. But if you're having fun, then and maybe learning something, then please remember to subscribe and like and comment. So until next time, stay tuned. Same bat channel, same bat time. Take care, y'all. Bye.